Okay guys, in this video segment we're going to cover our last type of concentration, which is molality, and then move on to colligative properties and how colligative properties affect solutions. So far we've talked about molarity, percent by composition, parts per million, parts per billion. We'll get into some other concentrations in the acid-base unit. What we haven't done yet is molality. Okay, it sounds a lot like molarity, but it is a different thing. Okay, so molarity, molality, very similar words, but you got to be able to keep those two things separate. Now with molality, we don't use this type of concentration very often in the world of chemistry because we're dealing with kilograms of a solvent, which most of the time we like to use volumes when we do solutions because most solutions are based off of water. Now however, there are certain cases where molarity doesn't work. Okay, molarity doesn't work whenever you have a temperature change through your experiment. And with molarity, because you're doing the volume of a solution, as temperature changes, the density of that solution will change, thus the volume would change. So if you actually change your temperature through an experiment, the actual molarity would be changing with that temperature, so it would be temperature dependent. Now molality is not temperature dependent. What we mean by that is that at any temperature or any change in temperature, it would be the same value. So we really use it anytime we talk about something called colligative properties, which we're going to go into in our next slide. Molality is symbolized by italicized lowercase m. We use lots of m's in science and chemistry, so just kind of keep track of them. Molarity, remember, was a capital M, so this is italicized lowercase m. If you're handwriting it, just write like a normal lowercase m, but just make it kind of fancy. And when we calculate molality, it's moles of solute divided by kilograms of solvent. Okay, so we're not dealing with solution anymore. It's moles of solute versus kilograms of solvent. So we can keep track of both the solute and the solvent in our molalities. Okay, we're going to do a quick practice problem just to make sure that we're comfortable with molality and make sure that we can actually solve and calculate things with molality. So here's our practice problem. How many grams of benzene must be dissolved in 500 grams of acetone to make a 1.25 molal solution? Okay, so go ahead and pause the video now. Try the practice problem using that equation and a little stoichiometry, and then we'll come back and I'll do the example for you. Okay, so our practice problem gives us 500 grams of acetone, so we know that's our starting point because that's a number that is a single label to it. And it also tells us that we have a 1.25 molal solution. So a 1.25 molal solution means it's 1.25 moles per every 1 kilogram of solvent. So that's what that's telling us. Now acetone is our solvent in this process. So this kilograms of solvent is kilograms of acetone. So we can use this to help us get from grams to moles. Now 500 grams, we know that there's 1,000 grams for every 1 kilogram. And we know now from this we can put into here, for every 1 kilogram we have 1.25 moles. And then this is moles of solute. So the solute in this case is benzene. Okay. So we don't really need a mole ratio because we went from solvent to solute within this process right here. So we go from 1.25 moles, and then we can say for every 1 mole of benzene, we get its molar mass, which happens to be 78.12 grams of benzene. Okay? So again, molality, molarity, they're concentrations, they're ratios, so they can be used in our stoichiometry. Okay? We have our grams, we converted from grams to kilograms, kilograms to moles, and then moles back to grams, because we can make that switch between our solvent, the acetone, and our solute, benzene, with this step right here. Okay? So if we do that, and we come back to the slide now, we see that here's our problem, and we get 48.8 grams of benzene. Okay? So that's molality. Now, moving on to our next topic, which is colligative properties. We want to deal with colligative properties within our solutions because anytime you add a solute to a solution, what happens is you end up changing some properties of that solvent. Okay, so water we know has a certain surface tension, has a certain boiling point, melting point, freezing point. It has certain amounts of hydrogen bonding to it. All those properties change slightly as you add solute. If you imagine, the solute particles actually kind of block the water from doing the hydrogen bonding properly. Okay, so you imagine a normal water solution has a bunch of water molecules all intertwined and synced together by these hydrogen bonds, okay, which works out really well. As soon as we start adding solute in, so we start adding in some sodium ions or some chlorine ions, what can happen is these chlorine ions and sodium ions start to disrupt some of this hydrogen bonding. And when you disrupt that hydrogen bonding, it changes what happens to your solvent. So some properties change. Okay. Now, one thing we need to be aware of is this is for non-volatile solutes only. Okay. So volatile. Okay. If you know a volatile person, it's probably somebody who's kind of angry and kind of change very quickly, kind of person. A non-volatile means it doesn't evaporate very quickly. Okay. So volatile solutes are things that evaporate on their own very quickly. Non-volatile means that they don't evaporate. Or another way of saying that is tendency to escape a solution. So salt would be a great example of a non-volatile solute because you dissolve it in water, it's going to basically stay in there. Okay. Ether, which is a very lightweight gas, organic gas, would be an example of a volatile solute because as soon as you try to dissolve it in water, it's just going to evaporate out very quickly, being a volatile solute. So we're really not talking about gas solutes here very much. It's more focusing on solids and liquid solutes in this idea. So one of the things that adding solute does to our solvent in terms of colligative properties is it changes the vapor pressure. So as you increase the amount of solute in the solution, the vapor pressure will decrease. Okay? So if you can imagine, water molecules have to work together to generate this vapor pressure, or basically they have to work together to push back against the atmospheric pressure at all times. So as you add solute particles in there, the solute particles mess that up. The solute particles get in the way of the hydrogen bonding. The solute particles kind of block the ability of the water molecule to generate vapor pressure. So because they block that ability, the vapor pressure of that solution actually goes down. Now the result of that is that we get two kind of key things that go from that. The first is we get a boiling point elevation, and the second thing we get is a freezing point depression. Okay. So if you think about it, because the vapor pressure has been reduced, what happens is the whole solution now needs more energy to bring the whole vapor pressure back up to a temperature at which it will boil. Okay. So if you can imagine a solution that normally has a vapor pressure of, let's say, if our solution at 100 degrees Celsius has a vapor pressure of 1 atmosphere, okay, and this is pure water, this will boil because we have at 100 degrees Celsius what atmospheric pressure pushing down is 1. When those two things equal, we boil. Okay. Now, if I add salt in here, what's going to happen is that salt is going to disturb this, and it's going to drop this vapor pressure down, so it won't be 1 atmosphere anymore. Maybe it'll be only 0.8. Okay. So at 0.8 atmospheres, it doesn't match the 1 anymore, and it won't boil. So how do we get more vapor pressure? Well, vapor pressure is linked to temperature. So as we increase temperature, we increase vapor pressure. So the salt has reduced the vapor pressure. So to bring it back up to match 1, we got to heat it up some more. So maybe we'll bring it up to 105 degrees Celsius. And as you warm it up, this number then can go up to 1 again, and it will boil. Okay. So what happens is the addition of the solute lowers the vapor pressure of the solvent. So to get it back to the point where it needs to boil, that 1 atmosphere pushing back on it, you need to make the temperature hotter or make it warmer. Okay? So the boiling point goes up. Now, the exact same thing happens at the freezing point, but it goes the other direction. So when you're cooling something down to freeze, okay, at some point those hydrogen bonds start to lock into place and they start to hold the water molecule stationary or just so it vibrates. As a result, we call that freezing. Now, if you have salt particles or sugar molecules or other solutes in there, those things disturb the hydrogen bonding. So they're not as easily locked into place. It takes less energy to get them to lock into place. So what you really need there is a reduction in temperature. So if you can imagine, normally when we hit this 0 degree point, we start to form these hexagonal water crystals, sort of shapes. That's kind of a pentagon. We sort of putting these crystals into shape. Well, these bonds holding it all together, those are hydrogen bonds. But if we have a salt molecule in the way here, that's not going to lock into place as much as it would before. It disturbs that. So as a result, what happens is, at this particular temperature, at 0 degrees Celsius, we can't lock these in place like we used to. So we have to cool it down even more, okay? So we got to get it even colder, so even with the disruption of this, we can still get all these particles to lock in place, even amongst those solute particles. So as a result, we got to bring this temperature down, and maybe it'll actually freeze at a negative 10 degrees Celsius instead, okay? So what happens is, you actually expand the entire liquid phase when you're dealing with colligative properties, okay? So if we take a look at this applet from Iowa State University, here's water, here is your solute particles. So let's just kind of start. Let's add in a lot of water, and let's just start. And if we look, okay, boiling point of water is 100 degrees Celsius, freezing point is 0. We'll get to these values in a minute. Okay, it's going to warm up. Okay, starting to see a few little bubbles as it warms up. And then once it reaches that point, or we're at 100 degrees Celsius, we will boil. So now we're at about 100 degrees Celsius, and we're boiling. Okay, so it won't change temperature here. It'll stay at 100 as it boils. So now we're boiling, particles are leaving, and that's kind of normal. However, if I do the same process, but I add salt in, let's say I add in 10 grams of salt into here and dissolve that. And now, oops, and now I want to get this to boil, okay? Again, it's going to warm up. Okay, we'll put this into a hot water bath. Notice the switch is set to hot. Normal boiling point for water is 100, but we put 10 grams of salt in. So as this thing warms up, we're at 73. We're not quite at the boiling point yet. We're getting really close, and we hit 100, but we go right past that, and it warms up even more. So if you look what's happening here, now the water molecules are trying to leave, but they can't all get out. Because if this guy's trying to leave right here, he's going to escape. Okay? No, he's not. Look at, they got blocked. So it's almost like the solute particles are actually blocking the boiling process from happening. So what you need to do is give it more energy, higher vapor pressure, to get them to actually leave that process. Okay? You can do the exact same thing for cold. If we flip our switch here to cold, and now we want to freeze this, we'll set the same thing up. We have water here and 10 grams of salt in here, and we want to freeze this down instead. We see that as it cools down, okay, normally it would freeze at 0 degrees Celsius, but here we are at 3, 2, 1, and we had salt in there, so we're negative now, and it's still not frozen. So if you look, they're trying to freeze, but again, they block the process. These solute particles actually can block that process of resolidification. They basically don't let the molecule solidify again. So to get it to happen, you need to reduce the temperature even more, or expand that liquid phase between there. Okay? So when you look at that, the result of your colligative properties is that this is your pure solvent, where we have our pressure, temperature. Remember our phase diagram here, our triple point, critical point. If we switch this and we add a solute to this, what actually happens to your solution, okay, from the original to your new, is you basically move the triple point down the line further away. So as you graph it, you actually see the triple point move this direction. So you have a smaller solid phase, a smaller gaseous phase, and you've expanded that liquid phase inside of here. Okay, so that's what you look at if you actually look at the actual graph of this. It shows how this expands. So at 1 atmosphere pressure, the original freezing point was here. Now we've dropped it to here, so it actually decreased in temperature. The original boiling point was here, and now we've increased it to here. Okay, so that is what colligative properties do for us. Okay, now we can calculate colligative properties. To do that, we need to have a constant, okay, or some sort of multiplier. So to do that, F dot P stands for freezing point and boiling point. All we can calculate is the change in temperature. So what you do is you calculate the change in temperature and then add it to the original or subtract it from the original. So to find the change in temperature for freezing, we take the constant of freezing times the molality. Not molarity, molality, because it has to be molality because we can't change temperature with molarity. So for example, if we look at water's Kf value, so it's constant for freezing, it's 1.86. So if you had a 2 mol solution and you had the Kf of 1.86, you take 2 times 1.86, and basically the result of that would tell you how much colder it would be to freeze. Okay. Now, there's one hiccup in this process. This is basically the effective molality. Now, effective, what we mean by that is number of particles. Okay. So if you have a mole's worth of sugar in solution, you get a mole's worth of solute. However, if you get a mole's worth of salt in solution, you get 2 moles worth of solute. So what happens is, because salt particles break apart into 2 separate ions, they get double the effect. Okay. So if you had a 1 mol solution of salt, what you really have is 2 mol instead of 1, because you have 1 Na, 1 Cl. Okay. If you had 1 mole of K3PO4, you end up getting 4 moles of solute. So you get a 5 or 4 times the effect with that ionic compound, because you get 3 K pluses and 1 PO4. Remember, PO4 stays together in the solution. All right. So if you take a look at it, if we're going to do a calculation here, let's just kind of do a practice problem together. Let's say I have a 2 mol solution of aluminum oxide in solution. Okay, so let's make it kind of a complex one. And I want to know what the freezing point is going to be for this solution, this 2 mol solution. Okay, so I know that my change in temperature of freezing is going to be my K freezing times my effective molality. Now my effective molality, though, is not 2, because I have 1, 2, 3, 4, 5 ions here. So I have 2 times 5. So I basically have the equivalent of a 10 molality solution. So that's the number that goes into our equation. Because we have, when this thing splits apart, you're going to get you're going to get 5 different ions. So if it's 2 mol, you actually have to double this. You end up with 10 ions in solution for that. Okay? So a 2 mol solution multiplied by the number of ions there gives us a 10 mol effective solution. Plug that into our equation, and now our change in temperature for freezing. We look up the Kf, which will be given to you, is 1.86. And that And that is going to be times our 10 molal. And the label for this is degrees Celsius per molal. So molality cancels, and we end up with degrees Celsius here. That doesn't look very good. Let's fix it. Degrees Celsius over molality. Molality cancels. So 10 times 1.86, well that's 18.6 degrees Celsius. Okay, so my change in temperature is going to be 18.6 degrees Celsius, which means my original freezing point of water was 0 degrees C minus that 18.6. So my new freezing point would be a negative 18.6 degrees Celsius. Okay. Now, if you can tell, this is why we salt roads in the wintertime. Because we take a salt, we pour it onto the ice, that salt dissolves into the ice and makes a solution. That solution now has a much lower freezing point. So essentially what we're doing is we're taking the ice and we're generating a lower freezing point so that now liquefies again and we remove the ice from our roads. Okay? The exact same effect happens if you boil. When you boil, what happens though is the temperature raises. Okay? So same math, same process. You have a different value for Kb. So for water it's 0.512. But exact same math, but you gotta make sure that you don't subtract it. In that case, you add it to your boiling point for that. Okay? So here's 3 practice problems you can do. So please work through these 3 practice problems, and we will give you the answer key for these 3 in a minute. But work through these 3 practice problems and make sure that you can understand and do colligative property or boiling point, elevation, freezing point, depression calculations. Okay, I'm going to give the answer key to all 3 of these now. If you would, please take the time to work them out before I give you these, because if I just give you the answer, it's not going to do you much good, and then we'll end the video. So I'm not going to give you the work, I'm just going to give you the numbers for these 3, and you can work it out and make sure they get you those answers for each one of these. Okay? If you're getting something that is half or a third of some of these values, keep in mind that you may not have factored in this effect up here of your different number of ions, okay, in terms of what goes on there. All right. If you have questions on this, please let me know. But that ends this video segment. Thank you.